Hello everyone. Welcome to the third video of week 4. In this video, you will learn the construction of a confidence interval for the probability of success of a binomial distribution. Let us return to the kidney stones example from the first video of week 3. We focused on the technique using laser pulses. Now suppose we give this treatment to n patients and let x be the number of successful treatments. In the example of week 3, a dataset was discussed concerning 236 treatments. In this example, x has a binomial distribution with parameters n equal to 236 and theta, where theta denotes the probability of a successful laser treatment. In the example, 215 out of 236 laser treatments were successful, which leads to estimate 0.911 for theta. Now, what can we tell a new kidney patient about the probability that the laser treatment will be successful? For example, if we repeat the treatment for another 236 patients, then we will likely find a different number of successes and therefore a different estimate for theta. Now, to account for this kind of uncertainty, instead of giving a point estimate, we set up a confidence interval for theta. Now let us move away from the example for a moment and explain the construction for the general setup. So let x denote the number of successes in n independent trials. X has a binomial distribution with parameters n and theta, where theta is the unknown probability of success. We want to set up a confidence interval for theta. As before, we start by trying to build a pivotal quantity by standardization of x. From probability theory, we know that x has expectation n times theta and variance n times theta times 1 minus theta. Now we standardize x by subtracting its expectation and dividing by its standard deviation. Does this give us a pivot? Unfortunately, it turns out that the distribution of the standardized x still depends on theta. Therefore, it is not a pivot. However, for large n, there exists an approximation of its distribution. From probability theory, you have learned that the following application of the central limit theme holds. Suppose x has a binomial distribution with parameters n and theta. When the parameter n tends to infinity, the distribution of the standardized x converges in distribution to a standard normal distribution. This means that for large n, the distribution of the standardized x can be approximated by a standard normal distribution. In this case, we call it a near pivot. We will use this approximation to construct a confidence interval for theta. Now let z alpha over 2 be the critical value of the standard normal distribution. This is the value such that it has probability alpha over 2 to the right. And so its mirror image minus z alpha over 2 has probability alpha over 2 to the left. Now if the normal approximation is valid, then the probability that the standardized x is between minus and plus z alpha over 2 is approximately equal to the corresponding probability for a standard normal random variable, say z. By definition, this probability for z is 1 minus alpha. And therefore, the same probability for the standardized x is approximately 1 minus alpha. Now, how can we extract a confidence interval for theta from this? Well, we can rewrite the event on the left-hand side using absolute values. And if we then square both sides of the inequality, this results in the following probability on the left-hand side. Multiplying both sides of the inequality by n times theta times 1 minus theta, and putting everything on the left side, we find the following probability on the left-hand side. Now, working out the expression inside the probability, this turns into a second-degree polynomial in theta on the left-hand side. Now, you may pause the video here and check that this polynomial has the following coefficients. Since the coefficient of theta squared is strictly positive, the polynomial is a U-shaped parabola. So, we are looking for an interval for which the parabola is below the horizontal axis. Now, when we set this polynomial equal to 0, we find two roots. The smallest root gives the lower endpoint of the interval, say L, and the largest root gives the upper endpoint of the interval, say U. So the statement that the U-shaped parabola is below 0 is equivalent to saying that the interval from L to U covers theta. Now, this happens with probability approximately equal to 1 minus alpha, so the interval from L to U is a confidence interval for theta with confidence level approximately equal to 1 minus alpha. Now, if we set up a 95% confidence interval for the probability of success for the laser treatment, we find 86.8% and 94.1% for the lower and upper endpoints of the interval. We conclude that we are 95% confident that the probability of success for the laser treatment lies between these two percentages. By the way, note that this interval is not symmetric around the point estimate for theta. Now, clearly, the manual derivation of this confidence interval is quite involved. To avoid this, we can use another variation of the normal approximation that more quickly leads to another large sample approximation. Now, recall the normal approximation for the binomial distribution. It turns out that if we replace theta in the denominator by its estimate, theta hat, the limit statement is still valid. So the distribution of this standardization of x can be approximated by a standard normal for large values of n. And therefore, also this standardization of x is a near pivot. Now, how do we proceed in constructing a confidence interval from this approximation? As before, the probability that the standardized x is between minus and plus z alpha over 2 is approximately equal to 1 minus alpha. Now, in this case, the two inequalities can easily be rewritten in this way by multiplying by the square root in the denominator. And from here, the two inequalities can again be rewritten in this way with theta in the middle. The lower and upper endpoint of the interval only depend on the observation x, and this random interval covers theta with probability approximately equal to 1 minus alpha. And this leads to the following confidence interval for theta with confidence level approximately equal to 1 minus alpha. Now, since x over n is equal to theta hat, this can also be written as follows. Now, note that this interval is symmetric around the estimate theta hat. And for this reason, the interval is sometimes briefly denoted as follows. Now, let us see how this works out for the kidney stones example. With alpha equal to 5%, we find the following confidence interval for the probability of a successful laser treatment with confidence level approximately equal to 95%. Now, we have seen two constructions of a confidence interval for the probability of success theta of a binomial distribution. Now, R has automated several constructions of such an interval, and we illustrate some of them by means of the kidney stones example. You have already encountered the R function binom.test in the first video of this week, which can be used to perform a test for theta. However, when running this R function for a two-sided alternative, the output also reports a 95% confidence interval. This is not one of the two constructions we just discussed, but another one based on yet another approximation. We will not go into this. The first interval we discussed, derived from the U-shaped parabola, can be obtained with the R function prop.test. To get exactly the same interval, one has to set the option correct to false. You may check that the output gives the same 95% confidence interval as the one we previously derived manually. Now, the default choice for the option correct in prop.test is true. In that case, the normal approximation for the binomial uses a continuity correction. Such a correction is to account for the fact that one approximates a discrete distribution, such as the binomial, with a continuous distribution, such as the normal. With the continuity correction, we would get a slightly different interval. Finally, the second symmetric interval we discussed can easily be made by hand. And here's the R code for this and the resulting interval. Now let me finish with a figure that contains the four different confidence intervals. They differ somewhat in terms of symmetry and length. The dot in the middle represents the point estimate for theta. Now note that none of them contains the value 78%, which is the probability of success of the classical technique for removal of kidney stones. So this confirms the fact that the null hypothesis that the laser treatment has the same success rate as the classical treatment is rejected at significance level 5%. This brings us to the end of this video, and see you at our next video.